Hey guys, welcome back to chapter 6 here. We're looking at the second and third sections here, work done by a varying force. First thing we'll look at here. And so for a force that varies, the work can be approximated by dividing the distance up into small pieces, finding the work done during each, and then adding them all up. As the pieces become very narrow, the work done is the area under the force versus distance curve. So for those of us in calculus, we understand what that means. It's the integral. Basically, though, we're just taking the area of the rectangles or the shapes that it makes under this particular curve. So notice that for the units of the area, we have the vertical unit, which is a Newton, a force, times the horizontal unit, the distance in meters. And so remember that becomes a Newton meter, which is the unit of energy or joules. And so that's what we want. We want this energy thing to happen. So an example that we'll be using here, here's our curve here. We have a force that was constant for 2 seconds, decreases for, let's see, 1, 2, 3, 4 seconds, and then is constant again for a second. And what we do is we take chunks. And so if we look here, we have the work done can be represented by the area of a rectangle. Area is base times height. So we have those two shapes there. And then we have the two triangles, 1/2 base times the height. So once again, the area unit matches energy, Newton meters. Above the x-axis is positive work. Below the x-axis is negative work. And so anything negative can be something taking energy away from the system. It could be friction. It could be an opposing force somehow. All we know is it's negative. It's opposing the motion that the object is undergoing. The total work done on the system is we add the areas. So here we say area 1 plus 2 plus 3 plus 4. And the calculation here is 6, 4.5, negative 0.5, and negative 1. That's just the area of those negative things. So when you add them all up, you get 9 joules of work done. You can figure out how much work done is individually. So you could look at individual things, and those could be individual forces somehow. But when you add them all up, that's the total work done on this particular system. Now, moving into kinetic energy and the work energy principle. So here we have energy was traditionally defined as the ability to do work. We know that's not necessarily the case. All forces aren't able to do work. So the centripetal force, because it's perpendicular to its motion, the example of us carrying something around, not lifting it up or down, doing no work on it, even though we're spending energy. So those are some interesting concepts we'll look into. But what we're looking at is an object moving. Basically, if an object is moving, it hits something else. If it moves something else, it is doing work. So it has energy due to its motion. That is kinetic energy. It's defined as 1/2 mv squared. We get that word from kinetikos, meaning motion. And here mass is, m is the mass in kilograms, and v is the velocity in meters per second. And so when we crunch those numbers or look at the units, we still get joules, a Newton meter. So if something's accelerating, we know there's a change in velocity, and so we know that work is done. So when work is done, we have this net work idea, where we basically take the final phase or the final velocity chunk and subtract it from the initial in terms of energy and see what happens. So I have my car, I have my green initial velocity v1 and then the applied force F net on it. It's going to be placed over a distance, and so we know the net force times distance, well, that's going to give me the work here. If I continue to look at the car at the end of that displacement, I have a different second velocity if work is done on it. In this case, it's going faster, so I put energy into the system somehow by using the applied force increasing the speed of the car. So that's how I know work was done on it. All this to say is that work done is equal to the change in kinetic energy. So I have my work, force times distance. It's equal to the change in kinetic energy, delta KE. And in terms of velocity, I have the second velocity minus the initial velocity in terms of the energy. And so if work is positive, the kinetic energy increases. My car went faster, if you will. And then if I have negative work, I am decreasing the speed. So for example, your brakes are taking energy away from your car. And your car obviously slows down, which is a decrease in kinetic energy. So before class, I'd like to have a couple of questions for you guys to think about. 1, can kinetic energy ever be negative? 2, if the kinetic energy of a baseball is doubled, by what factor has its speed increased? And then the last question here, if its speed is doubled, by what factor does its kinetic energy increase? All right. Thanks for watching. I'll catch you guys later. Thank you. Bye-bye.